Okay, so let's begin the session. So we solved, this was the problem which we discussed in the previous class. So in continuation with it, we will uh, look into the next problem, that is problem 8. Uh, in an interference experiment, the two slits are separated by 0.150 millimeter, and, and the incident light includes two wavelengths. So one is 540 nanometer, another is 550 nanometer. The overlapping interference patterns are observed on a screen which is 1.40 meters from the slit. Calculate the minimum distance from the center of the screen to a point where a bright fringe and the bright fringe of green light coincides with the bright fringe of blue light. Yes, please try. Yes, can anyone tell me how to proceed with this? Roughly, you have any idea how to proceed with this numerical?
Sir, we can equate the y term, that is n1. Let's take suppose n1 lambda 1, let's lambda 1 d1 divided by d equal to n2 lambda 2 d by capital D by d, and then we'll get a ratio of n1 and n1 by n2.
Okay. So the equation is d sin theta is equal to d tan theta m1 lambda 1, right? So that we know. So anyway, we know d is equal to y by L, that is m1 into lambda 1. So similarly, if you want to take for the interference maximum for the blue, so that will be the same. dy by L is equal to m2 into lambda 2. Now, for integers of m1 and m2, you have m1 into wavelength 540 nanometer, m2 into the wavelength 450 nanometer. So the ratio will be 6 by 5. I hope you got this. So what you are doing is, in an Young's experiment, you are using two wavelengths. So one of green and one of blue. And definitely you will see an overlapping interference pattern which is observed on the screen. So you need to find the distance from the center to the screen point where bright fringe of green light coincides with the bright fringe of blue light. So you have the expression for bright fringe for green light is d sin theta is equal to m lambda. So a small angle approximation we can incorporate. So in that case, we have d sin theta is equal to d tan theta m1 lambda 1. So since there are two wavelengths, I'm taking it as lambda 1 for green. And then you see here, then we all know that tan theta is y by L, right? In that case, d into y by L is equal to m1 lambda 1. So the same thing, the conditions is L, Y, and D remains the same. The only thing is you are changing the wavelength. So that is lambda 2. So for our convenience, so M1 will differentiate it with respect to green as M1 lambda 1 and for the blue as M2 lambda 2. So since this is a constant, that is slit separation, slit and distance is these are all constant, not varied in the experiment. Only thing varied is the wavelength. So this remains the same. So equating this, you will get what the ratio as M1 by M2 or M2 by M1 as 6 by 5. From there, anyone has got the answer?
So 2.52.
Sir, 2.52 centimeters.
2.52, sir.
Okay. So the smallest integers satisfying both equations are 5 and 6. So then we know that d into y by L is equal to 2 into 700 nanometer. Okay, so in that case, you will get y as 2 into 700 nanometer into L by D, or you get y as 2.52 centimeter. I think you are correct. I displays the previous steps also. If anyone has not noted down, please note it.
Sir, have you done anything before this sum today?
Yes.
Sir, before this sum, I wasn't there in the meeting. Have you done anything before this sum?
No. This is the
Okay.
first problem which you start.
Okay.
I hope you. This is 2,700 nanometer. Okay. So if you take in this equation, if you multiply, that is 540 into say 5 or this 450 into 6. So you will get the value of 2,700 nanometer. Don't get confused. It's not 2 into 700 nanometer. It's 2,700 nanometer. Okay. And once this is known to you, and only the unknown is y, so which is 2.5 centimeter. I hope all of you have completed.
Yes, sir.
Yes, Kushi and Divyansh, yes, you are correct. 2.5 centimeter is right. So please note. So as I was mentioning in the previous class, you need to solve some problems like problem number 3, problem number 5, 6, and 7. So I think 4 problems I have solved, and the remaining these problems are for you to look into it. So we have solved each different type of problems, and similar to this, you have a couple of problems in the chapter. which is already the course material given to you. If you're able to solve this, and just let me know if you have any difficulty in that, you can write to us, we can discuss it in the next class. So this is for you people to solve. Please look into that. So we have made a difference in the course materials. Some problems are made bold and some are not. That is, some of them will be discussed in the class. Some of them is for you people to work out. Okay. So in the last class, I hope there is no query. Any query in this numerical? I hope the time given to you is sufficient enough to solve this numerical. I presume. If there are no queries, then we'll move on to the next topic. I'll give a break. Okay, a 5 minutes break will be given maybe around 8:45 or so, in half of the class, and then we'll recommence at that time. Okay, so we'll continue till that time. So intensity distribution of the double slit interference pattern. So you need to look at an equation which can describe how the intensity is distributed in case of a double slit interference pattern. You can see the double slit, the arrangement is given over here, and we all know that along the screen you have alternate bright and dark fringes which are formed. All of the bright or dark fringes are of equal width, right? So this happens because, as I was mentioning earlier, we have chosen a condition that A is very, very less than the wavelength of light, that is neglecting the diffraction effect. So due to that, we can assume this equation will hold good. So we'll try to arrive at the equation for intensity. For this, we will consider two coherent sources of sinusoidal waves, which are arriving from slit 1 and slit 2. They have same frequency because they're coming from the same source, and of course they will have the phase difference. So the phase difference is because they are arriving from the two different. Suppose if we consider a point P, and obviously because of the extra path, the light, the wave which is coming from the S2 has to travel. So there exists a phase difference between these two waves. So let we describe these two sinusoidal waves as E1 is equal to E0 sin omega t, and E2 is equal to E0 sin omega t plus phi. Now, in order to, as we know, the phase difference arises basically due to the path difference involved in this. So, except at center where the phase difference is 0, where a bright fringe is formed, at all other places on the screen above the bright fringe, above the central maximum or below the central maximum, either side there will be a phase difference because of the extra path the way the waves have to travel. For instance, if you are taking at the upper portion of the screen, you will see that the waves arriving from slit 2 has to travel extra distance. Suppose if you take the lower portion, that is from below O, you will see that the waves which are arriving from S1 will have to travel an extra path compared to the waves arriving from S2. So there will be a phase difference between the two waves. So we have we'll write it as E1 is equal to E0 sin omega t, and E2 is equal to E0 sin omega t plus phi, where phi is the phase difference, which is related to the path difference by 2 pi by lambda. Here the path difference we already know, we have studied in Young's double slit experiment. The path difference is d sin theta. So the resultant will be E1 plus E2. So these two waves add up and produce some pattern. We will see. Let us assume let it be a maxima or a minima. Let us assume that the resultant will give rise to some intensity at this point. That's what we are looking at it at point P. We are looking at what is the intensity at this point P. So we'll sum up the two waves, and that means we'll add the two components, and we'll find the resultant of it. So we can take omega t as B and omega t plus phi as A. So we will put this equation in the form sin A plus sin B, which we can write it mathematically. We can write it as 2 sin A plus B by 2 and cos A minus B by 2. The resultant will be 2 E0 cos phi by 2 sin omega t phi by 2. So if you carefully look at this term, it looks like an amplitude term, right? So this is the amplitude term, that is amplitude of the resultant. Okay, so E0 are the amplitudes of the individual waves arriving from slit 1 and slit 2 respectively, and 2 E naught cos pi by 2 is the resultant amplitude term, and this again is a sinusoidal nature. Resultant is also a sinusoidal, so this is the amplitude of the resultant wave produced due to we are assuming the two waves. Okay, so generally if you take into interference, there will be n number of waves. It will be added at point P. Only not one wave will be arriving here. There will be n number of waves will be arriving at this point P and producing a particular fringe, maybe bright or dark. So this is the resultant of two waves, and this is the amplitude term. So once you know the amplitude, so getting the intensity is not difficult, right? So our aim is to find the intensity equation for an intensity which can describe the pattern on the pattern over the viewing screen. So we all know that intensity is that proportional to the square of the amplitude, right? So if you square the amplitude, we will get the equation as 4 E naught square cos square pi by 2. And we all know that if E naught is the amplitude of the wave 1 or wave 2 coming from slit 1 or slit 2, we can call it as I1 is proportional to E naught square. In this case, we have taken it as, please note, we have taken it, both the waves are having same amplitude. Okay, as mentioning in the initial classes, that for a good interference pattern, it should be of having same frequency, right? And they should have a constant phase difference, and preferably same amplitude is good to have a neat interference pattern on the screen. So here the amplitudes are chosen are equal, and if E naught is the amplitude coming from the slit 1, then the intensity will be I1 into so I1 will be the intensity, that is square of E naught. So we'll take the ratio of I by I1. In that case, we can write 4 E naught square cos square pi by 2 by E naught square. So we can write this as 4 I1, right? Cos square pi. So 4 E naught square cancels. We have I by I1 is equal to cos square pi by 2, or I is equal to 4 I1 cos square pi by 2, and we'll write 4 I1 as maximum intensity you can see on the screen. So we'll write 4 I1 as a maximum intensity on the screen. So we can write the final expression as I is equal to I max cos square pi by 2. And we know that we can write this equation. This is the equation which governs the which can describe the intensity pattern on the viewing screen. So we'll see how this equation will work. Before that, we can have the various forms of this equation. So we all know that phase difference is related to path difference. From that previous equation, so we can write phase difference is equal to 2 pi by lambda into the path difference. So in this case, it is already pi by 2, so the 2 get cancelled. So we are left with pi d sin theta by lambda. The expression. Alternatively, we all know that since the sin theta is equal to y by L, we can put the equation in the similar form, but under a small condition, that is for small values of theta, of course, which is valid in case of the interference. The values of theta will be very small. So you will see this the equations can be rewritten different. So this is one of the forms. This is another form. This is so all the equations, or maybe you will be able to use it when maybe you're solving the problems. Okay. So you can see here an interference pattern plotted with respect to the path difference. You can see this is a central maximum. Okay, this is a central maximum, and you have a first minimum here, and you have a first maximum here. Okay. So in the previous class, we are talking about when we say about first maximum, m always corresponds to 1. When we talk about it, first minimum, m will be 0. Okay. The order. Okay. So the first maximum, second maximum, because we already have a central maximum here, and we have a first maximum corresponding to m is equal to 1, and we have a second maximum is equal to corresponding to 2, and so on. For whereas minimum, you will get for m is equal to 0 at here. You don't have something called central minimum here. So m for a first minimum, m will be order of m will be 0. And if you notice one thing here, all the bright fringe are of equal intensity, right? All are equal intensity. The maximum intensity you can see is 4 times the I1. So all the intensity, all the fringes are of same intensity. So this holds good only if it is the diffraction effects are neglected. Okay, if you consider the diffraction effect, this does not hold good. That is what you are going to see in the next few classes, how the diffraction effect brings the changes into the interference pattern. Okay, till that we are assuming there are no diffraction effects because the condition which we have chosen that the slit width is very, very small. So generally, if you refer to the textbook, they say extremely vanishing narrow slits. So when we say extremely vanishing narrow slits, in the sense the slits is almost to get vanished but not vanished. So it's such a small opening. So you can compare to the wavelength, it will be A will be very, very less. So in that case, you will get all the interference bright fringes will be of equal intensity. This is an ideal case. Generally, in experiment when we perform, exactly may not be able to keep all the fringes equal, but it will be almost the same. Okay, so all the fringes will be, if you this is an ideal case. Okay, theoretically, this is one will predict if you neglecting the diffraction. We all know that we can't eliminate the diffraction completely from the experiment. There will be diffraction do exist, but that can be limited. So it can't be eliminated, right? So in that condition, there may be fringes which are moving away will be slightly less. Okay, it may be, for example, it may be slightly less, but for our visual sensation, you will not be able to make it from our eye. Will not be able to make the differentiate between those small changes in the intensity of the fringe. So using this equation, you can find out the intensity at any point. It is not only at this angle. So you can find out, even if you want to know what is the intensity at this position, you can find out using this expression. Okay, once you know the phase and path, and you will be able to describe what is the intensity at this region. That is, you want to know what is the intensity here, you can determine. What is the intensity here, you can determine. Even you want to know the intensity at this position, you can also determine. So this equation will govern the intensity pattern, which is seen on the screen. I hope it is clear. Do you have any query in this? Anyone?
No, sir.
Okay, fine. So, with please, this is a simple equation. You need to remember the two ways varying by phase. That is, E1 is equal to E0 sin omega t and sin omega t plus phi. Add these two ways, and then get the resultant. Then square the amplitude of the resultant amplitude term of the resultant wave, and then arrive at the equation for intensity. So you need not to memorize this. Just apply the concept. You'll be able to arrive at this equation. So with this, we'll take up one numerical, and then we will look into the next topic. So in a double slit experiment, let L be 120 centimeter and D be 0.250 centimeter. The slits are illuminated with the coherent light, which is 600 nanometer here, and you need to calculate the distance y, okay, above the central maximum, for which the average intensity on the screen is 75% of the maximum. So demonstrate the graphical representation is given on the right hand side to you. So maybe you take a few minutes, try to solve by yourself. Then I will discuss the solution to this problem. I hope I'm audible to you. I think my voice is clear.
Yes, sir.
Okay.
Yes,
So
sir.
I'm going very slow till you people get adjusted to my voice and the pace. So then we will slowly we will proceed. Okay. I don't mind taking 5 to 10 minutes. But more, I prefer that most of you are comfortable and you will be able to understand what I'm putting forward the things to you. So I would advise the students to join little early. I can understand that is at 8 o'clock. Uh, uh, if not, because I was taking the recap what was done in the previous class, right? So by taken 5 minutes time to see what was done in the previous class. So if you join, that will be really helpful to you because you'll have something what is discussed in the previous class and then you'll have a continuation. Otherwise, you'll be joining somewhere in the middle and you may find it little difficult. So I request the students to join at least by 8. As I already told in the first class, I would prefer by 5 minutes to 8 at least. Now I'm telling you, at least if you join by 8, it would be good. Okay. Now coming to the problem. So just let me know if anyone has solved. Let me know the solution. And yes.
Sir, 48 micrometers.
Yes.
48 micrometer.
48 micrometers. What about others? Anyone else has got the same answer? I think Arnav Mehra, right?
Yes, sir.
Arnav, right? Yeah. Yeah. So he has got 48 micrometers, sorry. Anyone else?
So 4800.
40. Let me check. Let's see the problem. So in intensity double slit interference pattern, we have as we are discussing just now, the expression for intensity is I is equal to I max cos square pi d sin theta by lambda. So you need to use an appropriate form of the equation to solve certain problems. So we know that for small values of theta, we can write it as tan theta. So I'll not be repeating the same, and we can write that as y by L, right? Pi d remains the same, and lambda remains the same. So this y by L is because sin theta is equal to tan theta, small angle approximation. So we can write this expression as y is equal to lambda L by pi d cos inverse of square root of 5 by I max, and it's already given here that central max, so that you have to calculate the distance y above the central maximum, so at which the average intensity on the screen is 75% of the central maximum. So here if we have let us say 100%, whatever the intensity you get is 75% of the central maximum. So I is given as 0.75 times the I max. So then you have to find out the y, at what distance you will get such an intensity, which is 48 micrometer. So one thing I would always suggest you is first choose an appropriate equation. Before that, look into the data which has been given to you. Then think about the appropriate equation you need to use to solve this problem. Then don't go to substitution at the initial stage itself. Reduce the equation to an appropriate form. Suppose if you want to determine y, first reduce that equation form of y and then go to the substitution. Substitution should be the last stage because this is where you can avoid the mistakes of calculating a parameter. Do the substitution at the end. So those who have not got the answer, I will look at it and make a note of it. Yes, anyone has any problem in this particular problem? Just let me know before proceeding to the next topic. Any student having a query on this numerical or anything which has been covered till now, feel free to ask. Okay, I hope all of you got the same answer or different one. So I would advise, as I was suggested in the initial class, so always keep a notebook. You need not to write down the entire question. You make a note of the question number and try to solve it. Okay. So later on, you can copy down the question in your notebook for your convenience. So I would suggest that it would be better if you keep a notebook and where you can work on it. So that will be easier for you to preparing and looking at making small note of it, which may not be entirely available in the slides. Okay. Shall we proceed? If you have no queries in this, shall we proceed? Yes. I hope I'm audible to you. Hello.
Yes, sir, you're audible.
Okay, fine. So, so with this, we have completed the two-slit experiments. Two-slit experiment, that is particularly the Young's double-slit experiment and the intensity pattern viewed in the two-slit experiment, and also we have arrived at the expression for the intensity which governs the equation for intensity, equation which governs the intensity on the screen. So in continuation with it, we also looked upon the conditions required for the stable interference pattern and the methods to produce the various current sources. With these fundamentals, we'll proceed further and take interference to the next level, that is interference from thin film. So you will realize at the end of this class what are the applications of interference and what is the necessity to look into the interference from thin film. So generally the interference effects are observed in thin films.
Sir,
Yes.
second chapter.
Not a second chapter. It's the same chapter. Okay. It's a continuation of it. That's the particular first part was Young's double-slit experiment. Okay. That we have completed. And it's numerical. This is the second, and then you have some more topic like Newton's rings and Michelson's interferometer. That is the next part. Okay. It's the same chapter. The chapter is not completed. Okay. It's the next part in the same unit. So the interference effects are commonly observed in thin films. A thin layer of oil on water or thin surface of soap bubble. The varied colors observed when white light is incident on such films result from interference of waves reflected from the two surfaces of the film. Okay. A simple example is, I think the rainy season is just got over in Manipal. About to, it's almost done with it. I think since many of you are coming from the different parts of the country, and in some cases the rainy season might have started. Of course, everyone might have observed on the road if there is an oil spill. Is it right that you can see the various colors whenever there is a sunshine is there, you'll see the colors will be different colors will be seen. That is basically because of interference from the film. What is the film here? A thin layer of oil. And you can see here a scoop which is taken on the soap water. You will see which is viewed in the sunlight. You will see different colors. Why the different colors is because, of course, the thickness of the film will not be the same. So that is why the thickness colors. And if you see the viewing angle also, of course, you will see that various colors. For example, if there is an oil slick which is on the road, if you just view at a different angle, you will see that the colors will be different. And the thickness is also one of the reasons is thickness is different. So we will say condition changes, so the color will be different. So What is thin film? So this is one thing. How thin is a thin film? So this is a question which everyone will be asking, and one should know is we can say a film is thin when the thickness is comparable with the wavelength of light. So we can roughly say we are talking about the visible light. So we can roughly say a few microns. That is order of the micrometer. So few microns, we can say it as a thin film. So there is no definition whether it is a 500 nanometer is a thin film or a 600 nanometer is a thin film or 700 nanometer is a thin film. So we generally say a film is said to be thin if its thickness is comparable to the wavelength of light. So that is, we all know wavelength of light. We are talking about the visible spectrum. It is between 400 to 700 nanometer. Okay. What will happen if the thickness increases? So if you increase the thickness of the film, then the coherence is lost. Can anyone tell me why it is so? Why can't you be able to see interference from thin film? Sorry, thick film.
Sir, because the velocity of light changes in medium.
So the fringe pattern won't be as observed.
Yes, why? Why? That is what. Because of course, when the coherence is lost, the fringe pattern will disappear. What could be the reason? I just want to know. Everybody has seen the soap bubble, right? I think if you observe the soap bubble in sunlight, you will see that different colors can be seen, right? That's all because of the interference. Why thickness plays a crucial role? I already given the answer here. The greater thickness spoils the coherence of light. I would like to know why, what actually happens when you increase the thickness.
So it will become a two-source interference.
No. Basically, if you, as I was mentioning, the waves get reflected from. If you take this, sorry, I'll change that. If you take this as a thin layer of film, okay, and this is a glass, okay, on the glass, just for a reference, okay. So you have two waves. One is getting reflected from the top surface of the film. Another is getting reflected from the bottom surface of the film. This is wave 1 and this is wave 2. Okay. The film here is in yellow color. So let us say a film, generally it will not be freestanding film. So it will be on some substrate, what we call on some material. Right? Basically, you all know that most of the lenses are coated with a film, right? So there is a film which is coated on a glass. Here the film is in yellow. This is the film, and the waves which are getting reflected is from the top. This is called the top surface of the film. This is from the bottom surface of the film. The ray 1 and ray 2 will undergo interference and produce a pattern. The different colors you are able to see. Please note this incidence is oblique, not normal. At some angle I have given. So what happens now? My question is, what happens if you increase the thickness? Because this is very crucial, because there are certain things we are going to discuss in this class. Then only we will be able to understand in solving the problems. Okay, anyone? Last chance I'll give before.
So does by any chance refraction take place?
Okay, so basically what actually happens is, if you widen the thickness, when the keep on increasing the thickness, we all know that two sources waves can interfere or superimpose if they are traveling side by side, right? True, right? If you keep on increasing the thickness, what will happen to the spatial coherence? So the two waves, which will be far up. If you keep on increasing the thickness, the two waves will be far apart. The chances that they overlap will be very, very less. So if you keep on increasing the thickness of the film, there is a loss of spatial coherence, of course. Then the temporal coherence also will be a difficult thing. So if you keep increasing the thickness of the film, so the two waves will be far apart to overlap. So the superposition can take place when two waves traveling side by side. They should be close enough. So for that, it's only possible if the two waves, the film is of a thin. If it is of a thick, then the waves will be far apart and they'll not be in a position to overlap. So then you will not able to see any interference pattern over there. Okay. So please note in setting up, we will be setting up an equation today in the interference from the thin films, equation for thin films. In that, we need to take into two things into consideration. So the first thing we need to look into it is phase change due to reflection. Whenever the light undergoes reflection, in some case, there is a change of phase. When does that happen? So we will discuss the two things. One is the phase change due to reflection, then the optical path difference. This is two things which you need to understand before setting up the equation for an interference from thin films. So before the break, so I will discuss one of the topic, that is change of phase due to reflection. So in general, if you take an electromagnetic wave, undergoes a phase change of 180 degree upon reflection from a medium that has higher index of refraction than the one in which the wave is traveling. So this you can take the analogy of reflected waves and the reflection of transverse pulse on a stretched string. So you can see here, one we have a rigid support, the other one has a free support. You will see the 180 degree phase change. That is, this is a incoming pulse and this is a reflected pulse. If you see here, in case of a rigid support, the pulse is completely inverted. It has undergone a phase change of 180 degrees. That is from a denser string, okay, of a rigid support. If the support is not rigid, you will see that observe this particular pulse, the reflected one will not be having any inverted inversion will not take place if it is freely supported end. And in this case, you will see there is a phase change of 180 degrees. This is an analogy between the stretched string and with respect to light. So similarly, in case of any electromagnetic wave, it undergoes a phase change of 180 degree if it gets reflected from a medium that has higher index of refraction. That is, so the wave which is traveling, if N1 is the index of refraction and N2 is the index of refraction of another medium, if N1 is less than N2, that is, it is traveling from rarer medium towards the denser medium, then there is a phase change of 180 degrees. If it is the other way around, if the light is traveling from a denser medium towards a rarer medium and gets reflected, then there is no phase change. So phase change happens from when there is a reflection getting reflected from a medium of higher index of refraction. We'll take few cases, so it will be clear to you in the next few slides. So this is just an example to show a simple animation which shows if there is a where there is an inversion is taking place and there is no inversion is taking place. You can see here what we have taken is you can take a thick thread and a thin thread joint. So when you set up a pulse at this interface, you can see here the reflected pulse. If you observe carefully, it is not inverted. Now you have a thinner thread and a thicker thread joint, and a pulse is set up. You will see that observe the inverted pulse. You will see here that is undergoing a inversion. That is, Whenever there is a electromagnetic wave traveling from a medium of lower index of refraction towards a medium of higher index of refraction, it undergoes a phase shift of 180 degree or a path of lambda by 2. So in order to put it in the simple terms, we can say when a light is traveling from a medium, that is air, we have taken the three cases: air, glass, and water. Okay, we know air is 1, the glass is 1.5, water is 1.3. Now, so we are looking at the reflections from the top surface of the glass and the bottom surface of the glass. So you see here, when the light is traveling from rarer medium towards the denser medium. So by looking at the refractive index, we can say at light getting reflected from the glass will undergo the phase change of 180 degrees or corresponding to path of lambda by 2. Now, so we all know that when this is a path partially reflected, partially transmitted, we can say it is reflected, transmitted in the sense it's refracted ray. And again, when it comes to an interface here, again it is refracted and reflected. The one which is coming out from this bottom surface of the glass in this case will undergo no phase change, because you should forget, see, the moment the light enters the glass, you should forget that it is not in the medium 1. Now the light is traveling in a medium of refractive index 1.5. So which is denser compared to 1.33, right? So now the light is traveling in a denser medium and getting reflected from the rarer medium. So there is no reflection phase shift here, getting reflected, and this position is only refraction. So phase shift takes place only upon reflection. So then the ray comes out. This does not undergo a phase change. So phase change takes place only when light is moving from a rarer medium to denser medium and gets reflected. We'll take few more examples. There are 2 examples here, so this will clear further. So you can see here, as a simple case, I was discussing about oil which is on the road, a thin layer of oil which is on the water, right? And please note, we are not discussing about the films. We are talking about the interference from the thin film. Here the film is oil. Now we'll take, this is wave 1 and this is wave 2. You can see here, incoming light falls on the top surface of the oil, gets reflected. We all know air is 1, below is 1.44. So at this position, I would suggest that mark the reflection points. That will be simpler way to identify the phase change. This is the top surface of the film. This is the bottom surface of the film. Always mark these 2 things. Once you have marked the point, keep the pointer here and take a pencil and position the pencil over there. Compare the refractive indices above and below. Above is 1 and below is 1.44. That means rarer to denser. So this will undergo a phase change of 180 degrees. Okay, that is wave 1. Now, then the ray further undergoes refraction and travels and getting reflected from the bottom surface of the oil, right? This is the point where it undergoes reflection. So you can see it is 1.4 and this is 1.3. Please note that the moment the ray enters, you forget that its refractive index is 1. The refractive index is now is 1.4. So below, at this point below is 1.3. So place the pointer here and see, compare the refractive indices above and below. Above is 1.4, below is 1.3. That is denser to rarer, so no phase change. So that means the ray will not undergo any phase change. So we'll take another example. You can see here, the film here is a silicon oxide. The silicon is a silicon oxide, and the thickness of the silicon oxide be T. Now we'll consider a ray of light entering, getting reflected from the top surface of the film and the bottom surface of the film. As I told, mark the top surface and the bottom surface of the film. You will notice here that the first one is undergoing a phase change of 180. Why? Because if you place the marker here and see, the refractive index is above and below. Above is 1 and below is 1.45. In that case, that is, the light is traveling from a rarer medium towards a denser medium, so it undergoes a phase change of 180 degrees. Now, Once it enters the silicon oxide, the refractive index is 1.45 and below is 3.5. That means this is rarer compared to this. So ray 2, which is traveling in a medium that is silicon oxide, is traveling in rarer medium towards a denser medium. Again, as I was mentioning, place the pointer and see that compare the refractive indexes above and below. That is a simple way to find out whether it's relative denser or to denser to rarer. Place the pointer here, it is 1 to 1.45, that is rarer to denser. Place the pointer here, compare the refractive index above and below. Above is 1.45 and below is 3.5. So when it is getting reflected and it comes out, the ray 1 and ray 2 has a phase change of 180 degree. In this case, you see there is only one wave is undergoing a phase change. Here in this case, you are seeing there are two waves undergoing a phase change. So reflection phase shift is a case where the light experiences a 180 degree phase change when it is getting reflected from a medium of higher refractive index, and there is no phase change if it is getting reflected from a medium of lower refractive index. Is it fine?
Yes,
Is it
sir.
fine?
Yes, sir.
Okay, so keep that in mind. Reflection phase shift, not refraction. Reflection, phase change upon reflection. So you need to concentrate on reflection from top surface of the film and the bottom surface of the film. You need to look at the reflections from the thin film. Okay, that is top surface of the film and the bottom surface of the film. So I hope phase change upon reflection is clear. So that is phase change upon reflection takes place when light is traveling from rarer towards the denser, not the other way around. A simple example is a Lloyd's mirror experiment. We all know that if you place a mirror and a viewing screen and you keep a real source, if you view from the point P, you will see that as if there are two sources are there. Generally, there is only one source. The other one is called S dash is the virtual source, right? So light will be arriving at point P, and another light wave will be arriving at point P, will be coming. Will be, if you see from here, it will be coming. It gives an impression that is coming from the mirror. Actually, it is not. So from it is due to the reflection. Please note, due to this second ray undergoes a phase change of 180 degrees. So on the viewing screen in Young's experiment, where you got bright fringes, in this case you will get dark fringes because one of the ray is out of phase, right? If they are in phase, you would have got bright. Since there is a reflection at here which undergoes 180 degree phase change, that is, it's inverted. So the two rays cancel each other and produce the dark band. So wherever you have seen the bright fringes in the Young's double slit experiment, at the same positions you will see dark. Wherever you are dark in the Young's double slit, you will see a bright. So that indicates that any reflected ray undergoes a phase change of 180 degrees. Okay. So this also confirms the change of phase of light waves upon reflection. So this is first thing you need to remember in setting up the equation for interference from thin film. So before proceeding to the next, I'll give a 5 minutes break to you. Now it is 9:02 and we'll join at 9:07. Okay, I'll give a 5 minutes break and we'll rejoin.
Sir. Hello, sir.
Okay, so I am back. So we'll wait for 1 or 2 minutes. If any students have query, you can please ask me. Yes. Any queries before continuing with the next? I hope I'm audible to you.
Yes, sir, you are audible.
Okay. Any queries?
No, sir.
Okay. So let's continue in that case. So that is, there are two things which we need to look into it. One is phase change upon reflection, which just now we have seen that the light ray traveling from rarer to denser medium undergoes a phase change of 180° across the path of lambda by 2 upon reflection. So the second thing we also need to look into is something called optical path. So we'll be discussing that. We all know whenever the light is traversing from one medium and moving to another medium, we all know that its velocity changes and accordingly its wavelength changes. The fact which remains the same is the frequency. So the type of interference in thin films is determined by the wavelength, right? So that is the wavelength in the film, not the wavelength in air. So it is necessary to write down the expression for the wavelength in the film of having a refractive index of n, and lambda is the wavelength of light in vacuum. So in that case, we can write lambda n is equal to lambda by n, or in simple terms, we can say the wavelength in a particular medium is nothing but the original wavelength by its refractive index. That is, when I say original wavelength, I'm talking about the wavelength just before it enter into the medium. So the wavelength in the medium will be is equal to nothing but the wavelength, the original wavelength by the index of refraction of the medium. In this case, it is the film. So it is therefore what is important here is the optical path length difference and not the geometrical path length difference while discussing in interference from thin films. So can you tell me what is the difference between the two things, the geometrical path and the optical path? Anyone? Can anyone just attempt? Please try and tell me what is the difference between the two. Yes.
Sir?
Yes.
Sir, my connection became a little weak, so your voice broke up. What was the question? Could you repeat again, sir?
Yeah, the question what I'm asking is, for us, it is the optical path difference is important than the geometrical path. What is the difference between the optical path and the geometrical path? That is what I'm asking.
Sir, maybe we have a pencil of 2 centimeters. If we keep it in a medium of refractive index 1 and in another medium of refractive index 1.5, the geometrical length will be the same, but the optical length will be different.
Yes, yes. So, so we will see whenever we talk about the path difference in optics, we generally talk about the optical path difference, not the geometrical path difference. As one of, I think you, a classmate, what's your name? I didn't notice. Who gave the answer just now? Okay, fine. I didn't notice. Fine. Okay. So he was discussing about the pencil. So we'll take up the case and we'll see what is optical path length. So optical path length for the light wave is the vacuum path equivalent of its geometrical path in the medium. What does it mean? For instance, I am considering the two cases AB and CD. That is, let us assume a medium having a refractive index of N, and a light ray is traveling in a medium of refractive index N. So it travels a distance of AB. In the second case, if there is no medium, it is a vacuum source, it travels a distance of dB. So the time interval is same, and if you see the line AB, it tells you the geometrical path. But so here the line AB shows the geometrical path, the length of the actual light path through the medium of refractive index N. The line CD is the optical path. It shows the distance of, let's say, delta, that the light would have been traveled in vacuum in same time t if N was not there. If it was vacuum, it would have traveled a distance of this. If it is because in the medium, it is the optical path, because of the medium of refractive index N, it could travel only a distance of b in same time. So in same time, you can try A and B. If the medium was not there, if it is vacuum, the equivalent path will be CD. So how to take into consideration of optical path whenever a refractive index of varying n comes into picture? Let us see. The distance traveled by the light in a medium in the time interval of t is d is equal to v by t, which we already know. And refractive index, as you know, it is n is equal to c by v, or v is equal to c by n. So we can say Ct is equal to nd. So what is nd? Nd is the optical path length corresponding to geometrical path length of d. So please note, whenever we talk in optics, we always say the path means not only d, n into d. Generally, in many cases, we don't write n because we assume that n is in A. So generally, we write it d. So you may have an assumption that it is d. So generally, in optics, we always need to take into consideration of n into d. It is something like if d is, let us say, 5 centimeters, if the same 5 centimeter length, in that suppose it's filled with water or oil or any other solution or air, so entirely there is a difference in the optical path, but d will remain the same. It is something like you have a person who, let us take any good athlete, is asked to run on a proper track, and again is let us say 100 meters, it covers in some time, and you are asking the same person to run on a track which is having, let us say, filled with sand. So obviously it will not be the same time. Within the same time, you will not be able to cover this. You will be cover the short distance. So there's the problem which is the sand. So here you always need to don't see the 100-meter track. You also have to see the medium. The medium medium here is n. It can be a water or a oil or any other medium which is having varying refractive indices. So refractive indices need to be taken into consideration for the optical path length difference. Don't see the geometrical path itself. So geometrical path is d multiplied by refractive index will give the optical path. So geometrical path and optical path are not the same. Geometrical path is d, optical path length is nd or nd. So optical path length for the light wave is the vacuum path equivalent of its geometrical path in that medium. So you need to multiply the geometrical path by n. I hope this is clear. Hope the difference between the geometrical path and optical path is clear.
Yes, yes.
Okay, so if you make a 3 tracks of 100 meters, forget about any athlete. You yourself, if you able to ask you to cover in, say, let us cover 100 meters. One is a proper track, another is filled with water, another is filled with sand. Definitely, you will see that there will be a difference in covering the distances, right? So we need to look into that's an analogy, okay? So don't take that as a real. Just for an example, I'm just giving it to you. So this n needs to be taken into consideration in optics. That is, whenever we say about path length in optics, it is the optical path length, not the geometrical path length. Okay. Now we know the two things, that is phase change takes place when light ray undergoes reflection from the denser medium, that is from traversing from rarer to denser, and does not undergo phase change if it is from denser to rarer. You can see here we are going to set up an equation for a thin film. Here the film has a thickness of T, and we can see here 1 and 2 are the reflected rays. Please note 1 and 2 are the reflected rays, 3 and 4 are the which are refracted rays which are coming out of our air. Okay. So we are talking about reflection, phase shift, and we are talking about the setting up the equations in case of reflection, that is for 1 and 2. So for this, let us consider a film which is having a uniform thickness, let us say T, and index of refraction is n, and if it is in the material medium, then the refractive index will be lambda n is equal to lambda by n. With this, three things, that is lambda n is equal to lambda by n and phase change upon reflection, and there is one more thing which I just discussed, with optical path length. We'll set up the equation for thin film interference. Okay. So probably this concept will be further clear when we start working on the numericals. Okay, these things will become, I can understand. You'll have some, not some confusion, a lot of queries will be there in your mind, how to choose the reflections and other things. This will become, this topic will be much more clear, become clear as and when we progress and we start with the numericals. To start with, when I say path difference, I was mentioning that it is the optical path difference. So the two ways, whether the ray 1 and ray 2 undergoes phase change, undergoes second thing. So what is the path difference between the two rays, lambda 1 and lambda 2 is, first thing is, it travels twice the medium, right? That is once, the first compared to the ray 1, ray 2 travels twice, right? Am I right? Two times it travels in the film. So it is 2 into T. And this is the front surface of the film and this is the back surface of the film. I always mentioned in the earliest class that you need to mark the top surface of the film and the bottom surface of the film. So keep the cursor here and see the refractive indices above and below. Above is air and below is film. So obviously it will be more than that. So from rarer to denser, getting reflected from the denser medium. So 180 phase change is there. The second one is, again, it is air. This is a denser medium. So the light is traveling in a denser medium and getting reflected from the rarer medium. So there is no phase change. If there is only one phase change, you can write 2T is the optical path difference. So between the ray 1, ray 2, what is the optical path difference? Ray 2 has to travel twice inside the film, whereas ray 1 has not at all traveled inside the film. So the optical path difference between the ray 1 and ray 2 will be 2T minus lambda by 2 into lambda n by 2, because there is a phase change of 180 degrees, so that needs to be taken into consideration. You may ask, sir, suppose if there are two phase changes. So if there are two phase changes, you can write it as minus lambda by 2n or minus lambda n. So generally, if there are two phase changes in the equation, we don't write because it gets automatically cancelled out. So you need to write it in the equation only if there is one phase change. Nothing wrong in writing the two phase changes. That does not going to alter your solution. So in this case, we have considered 2T minus lambda by 2 is equal to lambda n. And for in case if these two waves are undergoing a constructive interference, we know that 2T minus lambda by lambda n by 2 is equal to m lambda n. Or since we know that lambda n is equal to lambda by n, we can write 2nt is equal to m plus lambda is the expression in this case. Suppose if it is destructive interference. So if it is a destructive interference, then we can equate this equation as 2T minus lambda by 2, lambda n by 2 is equal to m minus half lambda n. This is for bright, this is for dark. So we can get the final expression as 2nt is equal to m lambda. This is the equation for thin film if the reflection phase shift is taking at one place. That is only at the front surface, not at the back surface. So please note, this equation is not the final. So depending upon each problem, you need to looking at the problem, you need to write the set of the equations. The simple way I would suggest is, first you can straight away you can write 2nt. That is 2 times the thickness is the compared to ray 1 and ray 2. Ray 2 has to travel twice in the film compared to ray 1. Ray 1 does not travel in the film, right? It gets reflected on top surface, whereas ray 2 travels twice in the film T and its refractive index is n. So write 2nt, that is the optical path difference. that's what I was always mentioning, the optical path. The second thing you need to bring into consideration is minus, look for if there is any phase change. Suppose there are both the cases no phase change, you need not write it. If there are phase change for one, then you write lambda by 2. Okay, I'm writing it straight away. Okay, because I have written already n here, so I have said that. So you can write that is equal to m lambda. So first look for 2nt. So ray 2 travel twice in the film of thickness T and having refractive index of n. Then look for is there any phase change by looking at the problem. Yes, if there is a phase change, write minus lambda by 2. And then based on the problem given to you, if it is bright fringe, write m lambda. If it is dark fringe, you write it m minus half lambda. Okay. If there are two phase changes, you can write twice minus lambda by 2 minus lambda by 2 is equal to m lambda, or you need not to write. You can straight away write if there are two phase changes are there, write 2nt is equal to m lambda. Okay. So you need not to you need not to write the minus lambda by 2 minus lambda is equal to m lambda, because next in the next solution will remain the same. If there are two phase changes, you need not write it in the equation. If there is one phase change, it may be from top surface or from the bottom surface. If there are one phase change is there, you need to write that in the equation. Okay. So we'll be solve one problem maybe today. Okay. Before going into the problem, we need to look into the some applications. What are the applications of thin films? So it is possible to suppress the unwanted reflections from the glass of chosen wavelength by coating the glass with an appropriate thickness. So you might have seen nowadays the spectacles which comes with anti-reflection coating cost you quite a lot. That is because a thin layer of coating which needs to be done over the glass, and that would be in a controlled manner. That technology itself costs you, it's an expensive one. So that's why the fabricating such a glass results in the high expenditure. So hence that is passed on to the customer whenever somebody goes for an anti-reflection coating glass. You all know the difference between the normal and the anti-reflection coating glass. It costs quite a bit. Of course, it has an advantage because it reduces the reflections. That is, then it will enhances the what you can say, the vision. In the sense, improves the quality of transparency. Moreover, they are also used in monochromators where they particularly transmit some kind of wavelength which is required. So they are used in monochromators. These are the some applications of thin film interference. Okay, if you look at this, what do you observe? Can anyone tell me? Hello? Hello? Can anyone tell me?
I can, yes, sir. CD player.
What do you CD player? Not a CD player.
Is
It's
it
a round glass.
reflecting
Yes?
internally?
Placing internally.
Well, the light is reflecting internally.
Sir, is it an anti-reflection glass?
Yes, yes, yes. So it's a, please note on a glass plate at the center there is a anti-reflection coating. Okay, and there is no coating on the other side. So because of the anti-reflection coating at the center, it looks like as if the glass is missing, but actually it is not so, because you can see the glare on the other side, but whereas at the center it's highly transparent. So it will ensure that most of the light which falls on the glass passes through it, not reflected back. When you see the glare, that is because of reflection. So that makes the difference. Another one example is you can see here. Suppose a person is wearing a spectacle with one as just for an example on a lighter note, one with having an anti-reflection coating, another without an anti-reflection coating. So it does make a difference in the quality. Quality in the sense it reduces the reflection and enhances the transparency. Okay. Do you have any query in this? Till now, what we have covered today, that is phase change upon reflection. You should know the two things in the equation of interference. When does the phase change takes place upon reflection, and what is optical part difference? And these two, if you are clear with it, setting up the equation is not at all an issue. Okay. Shall we take up one numerical today? I understand that time is over. Shall we do it today? If you all agree, it will be easier for you to understand the numerical.
Sir,
That's why,
sir,
huh?
sir. 10 o'clock we have another
Yes,
class.
sir.
Oh, you have 10 o'clock.
10 o'clock we have another class.
Okay, then
Sir,
we will.
we can do it ourselves later.
Okay, we'll do that. Okay, you can try this. I will discuss this on Saturday, right, at 2 o'clock. So then if you have
Yes,
10
sir.
o'clock
Okay.
class, then it's better not to disturb you because you already woken up at early and you have to have the breakfast also. Okay. And those who have any queries, please stay back. And those who don't have any queries, you can leave the channel. Have a good day. See you on Saturday. I hope if you have any issues, just let me know. Okay. If you have any
Yes, sir.
queries
Thank you,
pertaining to
sir.
the topics covered till today, you can stay back and get the doubts cleared, and then you can proceed. I'll be there for a few more minutes. If anyone has a query, please feel free to ask.
Thank you, sir.
Thank you, sir.
Thank you. Have a good day.
Thank you, sir.